right. So in the last segment, we just did a quick example of how to form an inverse from one of our algebraic functions from the previous course. And what I did during the break is I just simply threw this up and asked the class to form the inverse of this. Y equals e to the x. Be aware of what it looks like. Don't forget it. Looks like that, roughly. Right? Passes a horizontal line test. It's 1 to 1. When you form its inverse, it's going to look like, imagine rolling it over y equals x. Just let it roll. It's going to look like this. The horizontal asymptote on the exponential becomes a vertical asymptote. Y equals 0 becomes x equals 0. 0, 1 on the exponential becomes 1, 0 on the inverse.
It doesn't pass through the y-axis?
No. Does this one pass through the x-axis? No. As Stormy just asked, does this one pass through, or she was asking, does this one down here pass through the y-axis? Nope, because this one up here did not ever touch the x-axis. And notice what the range is, on this exponential. The range is greater than 0, isn't it? Greater than 0. And so therefore, that becomes the domain down here, greater than 0. We'll never hit the y-axis. So here's the math. Here's the original exponential. Here's the inverse of it by interchanging x and y. And then this is called an exponential equation. And if you simply write y equals here, recall what a logarithm is. It's simply an exponent. Y is equal to the exponent of e that yields x. When you apply e to some value, whatever that exponent is, you'll get this x reading. So we speak of this as a function because it passes a vertical line test, and we could label this, I called the original f of x. This is f inverse of x is the natural logarithm of x. Abbreviated, instead of writing log base e, we simply write it as ln, natural logarithm or Napier logarithm. Always remember when you see this, the base understood here is e. Okay, just a quick that was an additional comment about the inverse in algebra. Now let's look at trigonometry. Here's the reason we want to learn the inverses. Let's say I gave you y equals the sine of theta, angle theta. And let's say I told you that theta was, how about 1/2? What we need to find out is we need to be able to answer this question. We need to be able to undo the sine process of the angle theta so that we can write this as theta equals. It's no different than you having done a problem like this. Let's say you had square root of x equaled 5. What would you do in algebra to solve for x? You'd square both sides, would you not? And isn't that squaring process the inverse of the square root process? And what you do by doing that is you release this unknown that you were looking for and are able to then solve for it. That same idea has to apply to trig. So the terminology, I'm going to show you the graphical stuff here to make the connection back to what we just talked about, but the terminology we're going to use here now to release this angle and figure out what it is we're going to take the inverse sine of this ratio 1/2. In other words, we're asking what is the angle that happens to have a sine reading of 1/2? You have unit circle skills. right? You can answer this question, right? And you will get what for an answer?
Pi over 6.
Pi over 6 or 30 degrees. Are there any others?
Yeah.
Negative 11.
Are you thinking unit circle or are you thinking the graph of sine? How many are thinking unit circle to try to answer this? How many aren't thinking? Okay. Go back to unit circle.
So isn't it 5
Okay.
pi over 6?
Here's your 1/2 level, right? And you've got this angle, there's your 30-degree angle, right? And you also have one sitting over here, don't you? Yeah, and don't you have 2 pi possibilities added to this as well?
Yes.
Couldn't you be coterminal with this all the time at pi over 6 or 30 degrees? So you could think of this as adding 2k pi or 2 pi k to that. You see it written both ways. This is a general way of writing what that angle could be, and it's always going to be coterminal here, isn't it? Always going to be landing right there. If you add multiples of 2 pi over 6, you're always going to land right there and end up with a half. Okay? But there's another one over here, isn't there? 6 pi over 6, back off to 5 pi over 6. So you could say, or theta equals 5 pi over 6 plus 2 pi k. So you get an infinite family of answers to this simple question. Got it? Do you see how critical your unit circle skills are to be able to do this? And what we've just done is we've just really done an inverse problem. We've just solved a trigonometric equation where we have an unknown angle and we're able to then use our trig skills to be able to answer the question. And there's an infinite number of answers possible here. Okay. Let's relate this now to the graphical perspective. We all know what a sine graph looks like, and I'm going to use radian measure so that we're dealing with real numbers. So if I have 1, 2, 3, 4, minus 1, minus 2. So let's see, pi over 2 would be where in the domain here on a sine graph? Pi over 2. Think about it. Pi divided by 2. A little more than 1.5, isn't it? Okay, so I'm going to eyeball it right here. And you know that pi is right over here. Similarly, if I go up here in y, pi is going to be right up about here, and pi over 2 is right about in there. Real numbers. And similarly to the left, minus pi over 2 would be a little more than minus 1.5. So minus pi over 2 right in there, and then off to the left further would be minus pi. So all I'm doing is laying out a real number scale, both ways. And I tried to be equal on it. Yeah?
The variable k that you use in solving that, does that correlate to the k in the sine equation?
No.
It doesn't, okay.
No, because all this is understood to be here in the context of this, all this is understood to be is an integer.
Okay.
Thanks for asking or mentioning that. Because that's just an integer. Minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. Any integer. Right? Okay. Any other questions? Okay. Now, what I want to do is carefully, in a dotted form, like you saw me do a few minutes ago with a parabola, I want to dot a sine wave on there. I want to dot a sine wave on there. So minus 1 over here, let me do this. Minus 1 minus pi over 2 would be here, and the sine graph comes up through here, doesn't it? And then when you get over to pi over 2, it's going to be up here on its crest. And then as you continue past that spot, it's going to roll back down to its node, right? And then goes negative, continues on to the right and left, right? Check it out. Does it pass a horizontal line test? Huh? Is it 1-to-1? No, it's not 1-to-1. Right? Doesn't pass a horizontal line test. Up in here, it hits twice, doesn't it? And actually, if I keep going, how many times does it hit? How many times does it hit a half in value? Here, right? And over here, and out there, and keeps on rolling, right? And off to the left, right? Doesn't that sine wave, doesn't that thing hit an infinite number of values? Look back at this problem. Aren't there an infinite number of angles? 30 degrees, 150 degrees, 360 added or subtracted from it, multiples of 360, right? Infinite number of spots. That thing does not pass a horizontal line test. Okay, so what do we want to do? Restrict its domain. What looks like a convenient domain restriction to lay on this so that it does make it 1-to-1? Yeah, nice. I like it. So let's make this solid and not go past that crest or trough to the right or left. Right? Not too bad. Okay. Let's now form, I'm plotting some points so I can get a nice drawing here. If I wanted to draw y equals x carefully on this scale drawing, it's going to look something like that, isn't it? Y equals x. Now what I want to do is I want to take this line with a restricted domain and I want to roll it so that it has a restricted range from how low to how high. If I restricted this domain, now that becomes the range, right? Negative pi over 2 to pi over 2. And so the graph is going to look like, do I have another color? I don't know if that's going to show up very well. Let's try it. It's going to look like this, I think. Actually, might be a good idea to plot some points, right? Right? 0, 0 is easy. I can handle that right there, right? That stays there, doesn't it? If you interchange the x and the y. And this point over here was at negative pi over 2 comma negative 1. And this point up here was at pi over 2 comma 1, right? If we interchange those, then we're going to get a point that's going to be sitting right down here. And look at that. See that? Look at. You with me on this thinking? See how those points work their way across perpendicular to this 45-degree line symmetrically? Symmetrically across that 45-degree line here. And to get these other points, and this point down here is going to be then at negative 1 on x. Look at the picture. Negative 1 on x and negative pi over 2 on the y. And the other point up here becomes 1. X equals 1, and we're up at pi over 2. And you can see pretty accurately on my hand sketch here that seems to fit fairly well. And so what we get is a graph that looks like this. The red thing. And what I'm going to do is I'm going to draw it here for you in an expanded format so you can see it, and it goes as high as pi over 2 and as low as minus pi over 2, and it has a restricted domain from minus 1 to 1. This graph is called the inverse sine of x. And what you want to be aware of is this value right here is your ratio reading. Your input is a ratio reading. What's the output? What's this result? Physically, it is a, look back at the example, it's an angle, folks. It's an angle. Look back at our example we started with. When you do inverse trig functions, your result you're getting is an angle. What is the input is a ratio. This takes your brain and turns it around and runs it the other direction. Okay. New graph. New graph. See it? Right? And do you have a domain and range sitting right here? Yeah. You have a domain of ratio values from what? Ratio values from?
-1 to 1.
-1 to 1. And you have a range values of angles, right? Negative pi over 2 to pi over 2. The reason you have that, and notice they're closed intervals, they include the endpoints. The reason you have that what was I trying to say regarding that? Oh, yeah. The reason you have that is because for this thing to be a function, it can't roll back on itself and continue to wiggle up the y-axis, which is what would happen if I took the original dotted curve throughout its entire domain and I turned it, interchanged the inputs and outputs. It would just continue to roll up. And what you're seeing over here when we wrote this general solution down is there's an infinite number of angles coming out here, which are those other points that would show up if you chose an input of 1/2 here. You're getting back pi over 6 here, which we had easily. And if you let it roll higher, see how that graph would continue to roll on up here, and you'd get 5 pi over 6 up here at 1/2, and keep on going, multiples of 2 pi added to those. Okay, so that's what's going on here in trigonometry. And so what we have to do with all of our trig functions is we have to restrict the domain of the original function because they repeat themselves, don't they? All 6 of them? All 6 repeat themselves, so what we have to do is apply a restricted domain to be able to see the inverses. So this is kind of an introduction to the inverse stuff. When we do our next session on Friday, we're going to actually practice with these on some problems. And what I want to show you is a little bit with the calculator right now. We have a few minutes left. And I want to show you that the calculator is capable of handling this as well. So with the calculator, any questions so far on this? Okay. I'm going to show you both the sine inverse and the cosine's inverse, and I think I even have time to show you the inverse tangent. And I think what you could do is just sketch them in your notes if you wish to. So first of all, I'm going to check the mode. I'm going to go into, let's stick with radian mode, since that's the way I was doing this earlier, okay? So we're going to stay in radian mode, and what we're going to do is I'm going to build a viewing window first. And I'm going to go from -3 to 3, 1, and vertically from -2 to 2, 1. These 6 numbers. This is going to be a relatively undistorted sketch. Now, let's go to y equals. So on your sine key, what we want the outputs to be, think about what we're doing here. We want an output called y to be an angle. To be an angle. When we know the inputs to be the ratios, okay? And the sine ratios. So I'm going to use the inverse sine key by using the second or shift key on the calculator. So I get the inverse sine function, and my input is going to be x. And I'm now going to go ahead and hit graph. And there it is. What you can observe is here's -1 on the input. That's as far to the left as it lets it go. It can't find anything further out. Just like you know on your unit circle, right? The ratio values can't be outside the bounds of -1 to -1 to 1. And what you're seeing here is a graph that goes up about as high as pi over 2, even though it doesn't quite show here because it couldn't draw that next pixel up there because it's going to be so close to this reading. Okay, so watch, I can turn trace on though and get pretty close to that. If I turn trace on and I go pi over 2, that should work, shouldn't it? Oh, hold on, I'm sorry. What do my inputs have to be, folks? Stay with me. My inputs have to be ratios, values, right? I can't exceed 1, can I? So if I put 1 in there as my input and hit enter, look down here. There's pi over 2 right there, approximately. Okay, and there's that point that we just talked about. The coordinates are 1, the output is pi over 2, the angle. If I picked a half as my input, this is pi over 6. Think about the value, pi over 6. A little bigger than a half. Okay? So it's a function, new function for you. Okay, let's have a little more fun. Let's just change this range a little bit from -2 to 2 to say -2 to 4, 1. And now I'm going to change the function to be the inverse cosine. Now think, first of all, use your brain. Think about the graph of cosine. If you take the graph of cosine, you know it starts on a crest. It starts on a crest and drops off. Is it 1 to 1 as we progress, dropping off on cosine? Yeah, it's 1 to 1, isn't it? Until it gets to its trough. You can't go past that trough, right? So what's the domain restriction for cosine that you need to use? On the crest, it's at 0 degrees.
0 to pi.
0 to pi. To get it from crest down to trough, and then you form the inverse, and you're going to get a graph that wants to roll up the y-axis. So let's see what the picture looks like. Here it comes. See it rolling, wanting to roll itself up the y-axis there, up and down the y-axis. And so these are angles from 0 as high as pi. So if I went in here with an input of 1/2, I'm going to get 60 degrees, or pi over 3. Think about the cosine of pi over 3. Cosine of pi over 3. Here's my stick. Pi over 3. Right? The cosine reading is 1/2. So on the inverse graph here, you observe, here's your input, your ratio value. Here's your output, pi over 3 radians. Slightly more than 1 radian. What's your tangent graph remind you of from algebra? Tangent? Tangent reminds you of from what from algebra? X cubed, doesn't it? What's the inverse of x cubed? cube root. Remember what that looks like? I hope. Looks like this. Inverse tangent. Cube root graph looks kind of similar, except what's distinctly different about this than your cube root graph? Here's a hint. It's got asymptotes. It's got walls on the bottom, or floor on the bottom, and a ceiling on the top. Right? Because those vertical asymptotes become horizontal asymptotes. Getting the idea? And if I went in here with an input of ratio of 1, look at this. If I come in with an input of 1, I get an output of pi over 4. Pi over 4 is a little bigger than 3/4. Think about it. Pi over 4, right? A little bigger than 3/4. Here's the result right here, pi over 4. Okay, that was an introduction to inverses, and we'll continue on Friday. You folks have till this afternoon, I think at 3:20, to get that quiz done, the 25-pointer that's in the resource center.